So now it's time to begin solving the Schrödinger equation for a different kind of potentials, and we are going to begin by what is called the delta potential. Now this is quite long, so I'm actually going to divide this into several videos, and we will begin in this one to talk about this delta potential, but looking at what is called the bound states. Okay, so if you don't know what bound states are, then I really suggest you go back to the previous video where I discuss this topic. So okay, we want to solve this equation for the delta potential. So what exactly is this? So these delta potentials have the form of some constant times the delta function. Now this can be either plus or minus alpha. We are going to begin taking a look at the negative cases, right, at the negative alphas, and that is because, as we will, I will talk about that more in a future video where we talk about the positive alphas. But the reason is, just to let you know, that only the negative case will have bound states, and solving for bound states is much easier than for the scattering state. So we want to go first bound states and then scattering states. So in order to do that, we have to begin with the case of negative alpha, and later we can discuss what happens in the positive case. Okay, so that's also why in many textbooks they begin discussing this case, even though they don't always state the reason. So, and just in case anybody doesn't know, this delta function is basically just something of infinite height located at x. So in this case, this would be if it is a positive alpha. If it's negative alpha, like in this case, it's just going to be this spike with infinitesimal width and infinite height, and its area is going to be 1. And one of the properties is that if you integrate delta x, right, it's just going to be 1. And if you integrate delta x times some function of x, because this delta is 0 everywhere except at x equals 0, this integral is just going to be f evaluated at whatever point this is. In this case, if it's just delta x, it's going to be 0, right? But the delta could be shifted, but it doesn't matter. So that is the whole idea. Because the integral is basically a summation, and delta is 0 everywhere except at this point x equals 0, then the only term that is not 0 is going to be f0, so the sum is only going to be f0, right? So that's the important properties. And for what can we use? Why is this potential important at all? Why is it interesting? Well, because of its shape, you can, and the fact that it's localized at some place, you can actually use it to model, for example, the behavior of diatomic particles, right? You can put 2 of these, or even you can put several potentials, right? Delta potentials, and you can model, at least in a very simple way, some sort of lattice of atoms. So there's actually quite a few applications that can be interesting. So that's why it's important to just make sure to actually take a look at this. So let us now begin solving the Schrödinger equation. So what we have to take into consideration here, right, we got our x, this plane of x, this is going to be our potential of x. So in this case, we have a potential, right, I'm going to erase it so it doesn't, it isn't confusing. So our delta potential will be negative right here at x equals 0. So now we must remember, so there's 2 regions of interest here, because this is at x equals 0. It's going to be region 1, right, which will have a wave function psi1, which is going to be to the left of x, and there's also going to be a region to the right of x. So we're going to solve the Schrödinger equation for every region that interests us, and then we have to put them together by using the appropriate boundary conditions. They're going to be basically the same thing that you have seen in I hope your wave courses, right? And so you have to see that the wave itself is continuous and its derivative should be continuous. And if it isn't continuous, then you have to see what is it that makes it discontinuous. So that's what we're going to be discussing. And one final thing that we need to take into consideration is that, as I said, we are looking first for bound states. Later we will discuss the case of scattering states. So what is the difference? Why do I say we have to solve for bound states? So the reason is that the energy in the case of bound states will be negative, right? So here this potential is negative as well. So the energy of our system will be somewhere down here, right? So we are going to get some sort of wave that, as you will see, will look something like this. So that's what we are going to go for. So let us now solve the Schrödinger equation for this. So we got the equation, which is minus h squared divided by 2m d squared psi dx squared plus the potential, right, of x dx. Well, if I already wrote of x there, I kind of have to do it everywhere. And this is not dx, sorry, this is psi of x. Psi of x equal to e psi of x. Okay, so let's begin in region 1, right? So in region 1, just 1, that's just a 1, not an I, right? Region 1. So all of these psi's will be psi 1, and psi 1. So in this region, there is no potential. So this whole thing there is just 0. So we have to solve this equation. Now, let's, as usual, isolate our d squared psi dx squared. This is equal to minus 2m times e divided by h bar squared psi 1. Okay, so usually what we do here is that we define this right here to be k. So we say, okay, so k is going to be the square root of 2me divided by h squared, so that this whole thing is just k squared, right? But the problem here is that our energy is negative. So if we do this, we're going to get something negative inside of the square root, and that is not really something that we want at all. So instead of just calling this k, we're going to say, okay, so k is also going to include this minus sign. So now there's going to be a minus in here. So now this energy is negative, but there's also this minus sign. So the interior here of the square root will be positive. So k squared, just to make sure it's clear, is going to be minus 2m times the energy divided by h bar squared. So let us now substitute that in here. So we get this. So let us now put everything to the left side to solve this differential equation. So we get d squared psi 1 dx squared minus k squared psi 1. Now this looks very similar to what we have solved in the past, but this time there's a minus sign. Before we had this plus sign. So the solution will now be somewhat different, because now when we, well, obviously you can use whatever means you like to solve this. I like to do it like this, as we have discussed before, just expressing this as a multiplication of these two products right here, psi 1. So from here we got these two differential equations that will give us the two linearly independent solutions. So from the first one, for example, we just get that d psi 1 dx is going to be equal to k times psi 1. So from here we get then that the psi 1 divided by whoops, I was supposed to write psi 1 is going to be equal to k dx. So here we just integrate and then we apply the exponential. So we see that psi 1 is going to be some constant times e to the kx. And similarly, when we solve this, it's basically the same but with a different sign. So we're going to get that psi 2 is going to be equal to b e to the minus kx. So those are our two possible solutions. So the most general way to write the psi of the first region, right? So let's just write this rather than 1, just this Roman 1. It's going to be just the combination of our two possible solutions. So this is then our solution for the first region. And in fact, the solution for the second region will be exactly the same, but obviously with different coefficients, because the equation will be the same for both regions. So in this case, there's not really much of a difference in one region or the other. But what we have to take into consideration now is that in region number 1, x is going to be negative, and in region number 2, x is going to be positive. So in order for our solutions to be normalizable, these things have to go to 0, the solutions have to go to 0 as x goes to plus or minus infinity. So in the case of minus infinity, this term right here is going to be positive, right? Because minus minus, it will be positive, and this goes to infinity. So this part right here is not normalizable, so we have to discard it. It is not a physically acceptable solution. And similarly, when we are in the positive region, this right here is going to go to infinity as x goes to infinity. So this also has to be discarded because it's not a physically acceptable solution. So our actual solutions for regions 1 and 2 are what we see right here. Okay. Actually, well, I guess I should have just left it. This is x smaller than 0, x greater than 0. So those are our solutions. Now let us begin using the border conditions, because we know, well, actually, maybe I can just write it in a way that uses less space. So just put it like this. Side 2 is what letter was it again? D? Yeah, D. D e to the minus kx. Okay, so our two conditions usually are that psi at region 1 evaluated at x equals 0, which is where our two functions touch, has to be equal to the second wave function evaluated at x equals 0. This makes sense, right? Because if we have some wave function in two regions, we can't really expect to have our wave come in whatever form and then just start off somewhere else, right? It can't have these jumps. So it has to be continuous. That's what this first thing said. If the wave function arrives at this point, then it has to begin at that point. I don't care if it now does something else, whatever. But if it starts there, if it ended there, it also has to start there. Okay, so that's what this first condition says. Now there's a second condition that applies actually for finite potentials, but it says that also the derivative with respect to x of this first function evaluated at x equals 0 has to be equal to the derivative of this second function evaluated at x equals 0. And that also that's because if we have some function and then you get to the interface, it needs to continue smoothly into whatever thing it will change to. You can't really have something that just goes suddenly like in a non-continuous thing. Like if you zoom that, you can't really have something like that, right? Where it's not continuous. Or not continuous, but the derivatives are not continuous. That's what I mean. The function is continuous, but the derivatives have to be continuous as well. That applies for finite potentials. Now, we are dealing with a delta potential, so this condition will be somewhat changed. There will be a discontinuity. So this applies for finite potentials, and we will be applying it at other points. I just wanted to remind you of this because you may have seen it in some wave courses. So the second condition, this is condition number 1. The second condition we will actually get back to in just a minute. So let us begin just taking a look at this. So when we replace here our functions, we get a times e to the 0, which is just 0. I mean, yeah, 0, so this is just 1. So a is going to be equal to d. Right, so that's the first thing. So let us now rewrite actually our function. So psi in general now for the entire space is just going to be a e to the kx plus this other a e to the minus kx. But this right here is valid for x less than 0 only, and this is valid for x greater than 0 only. So we can actually put all of this together as a times e to the minus k times the absolute value of x. Because now, if x is going to be positive, you can just take the square root away, and it's going to be the same thing here. And if x is negative, then you have to replace it by minus x, remember? So it's going to be the positive that we see here. So actually we can write this into this form right here. It's not actually necessary for you to do this, but it will be a bit easier to integrate later on, and it's also more concise. So as I said, if you didn't think of this as you were solving, it doesn't really matter. You can get to the exact same result, but it is nice to know it and to use it. Okay, so now we have to begin thinking about the second condition, as I said. So we want to know what is the deal with the derivative of our function evaluated in the negative region, as right when x begins being negative, which is basically 0 from the left, right? Basically 0 from the left. And what is the deal? How does it relate to the derivative, but coming from the right? So if we have our discontinuity here at 0, we want to know what's going on as we approach from the left and as we approach from the right. So where could we find an expression that gives us this information, right? Where can we find something like this? So now, obviously, this is somewhat of a trick. So if you didn't think of this the first time, really don't worry, that's perfectly normal. So the Schrödinger equation has this d squared psi dx squared. So if we were to integrate this from some very small infinitesimal number, epsilon, right, from negative epsilon to positive epsilon, and then we make that epsilon go to 0, we could actually find exactly this, because if we integrate this from minus epsilon to epsilon dx from a fundamental theorem of calculus, this is just going to be the derivative sorry, the derivative of psi with respect to x evaluated at this point right here, which is going to be the positive part, epsilon, minus this derivative with respect to x evaluated at minus epsilon. And that's what we want. We want to relate these two things, right? So as we can see, the Schrödinger equation seems to have the answers if we integrate it. So let us do precisely that. Okay, so let us now integrate the Schrödinger equation. So the first term is minus h bar squared divided by 2m times this derivative right here, so that's already done. Then we have the potential term. So then we have minus, whoops, sorry, I was going to write that again. So the integral from minus epsilon to epsilon of our potential function of x times psi of x dx. This is going to be equal to the integral from minus epsilon to epsilon of the energy psi of x dx. So this is what we now have to solve. Now it may look daunting at first, but don't worry, because this is going to be actually a lot easier than it looks. So let us begin by analyzing this term right here. So first of all, the energy is just a constant, so we can just go ahead and take it out of the integral. The energy does not depend on x. So then we just have to integrate this function. But the thing is, this function is going to have a limited height, right? It's just going to be, you know, we have our graph, well, actually it's going to be almost covering up, but it will have some height, right? But the thing is, our epsilon, which is the width, is going to go to 0. So that is going to dominate over whatever height this function has. So this is just going to go to 0 because our limits are going to be vanishing. So this whole integral here is just going to be 0. So that is the first term. Then we have this right here. So what is our potential? Our potential, as we said, I'm just going to put, is minus alpha times delta x. But alpha is just a constant, so we can put it outside of the integral. And then we have the integral of delta x times psi. But we know that the integral of some function, right, times this delta function is just going to be the function evaluated at the point where delta is not 0. So in this case, it's just going to be psi of 0, because delta is only not 0 at that point. So actually, this whole integral is now just going to be psi of 0, right? So it's actually looking quite good already. I'm just going to put this a bit all together here. Okay, so all that now remains is to determine the integral of this first term, but as we discussed at the beginning, this is just going to be this discontinuity of the derivatives, right? Because this is going to be minus h bar squared divided by 2m, and this is the reason why we decided to integrate the Schrödinger equation in the first place, because we wanted to get the d psi dx evaluated at epsilon minus d psi dx evaluated at minus epsilon, because then when we take the limit of epsilon going to 0, this is just going to be the derivative with respect to x from the right side, and this is going to be the derivative with respect to x from the left side. So if the derivatives were continuous, then they should be the same and this thing should be 0. So we can, with this, actually evaluate and see if there is any discontinuity at all, and if there is, what it is. So this is going to be equal to this right here, which we can now add up. So it's going to be alpha psi times 0. Okay, so let me now copy this, go to the next page. So now we can just multiply by this minus h bar squared divided by 2m and put it here as minus 2m divided by h bar squared. And with this, we can now just call these derivatives right there. They are going to be, as we said, this discontinuity. So we just write this delta evaluated at x equals 0, right, when epsilon goes to 0. And this will just be minus 2m divided by h bar squared times alpha psi evaluated at 0. So now we need to find psi evaluated at 0, and we need to find this discontinuity. So in order to do that, we only have to compute these quantities. So psi evaluated at 0, we know that psi is going to be just our constant a times e to the minus k absolute value of x. So if we evaluate this at x equals 0, then this is just going to be a, right? And now d psi dx, let's take a look at this. So when we do this derivative, it's basically this function right here. I have to put here that this is evaluated at x equals 0. So when we take this derivative, we have to take into consideration that this first part, so let's put it evaluated at epsilon, this is going to be the region where x is positive. So what we are deriving here is d by dx of a times e to the minus kx, right? So this term is just going to be minus k times a e to the minus kx, but we have to evaluate this at epsilon. So this is just going to be times epsilon, and in the limit where epsilon goes to 0, this is just going to be, oops, minus ka. And now if we do exactly the same thing, but for the other derivative, so evaluated at minus epsilon, now we have to take this absolute value to be minus x. So we get a e to the kx evaluated at epsilon, and well, we have to take this derivative, of course, we haven't done that yet. So this is going to be a times k times e to the k epsilon, and as epsilon goes to 0, this will just be a times k. So this discontinuity then, delta x equals 0, this will just be, remember, what was this? This was this first part, the derivative evaluated at epsilon, which is minus ka, minus the other one, which was ka. So basically, we're going to get minus ka minus ka. So this is just minus 2 times k times a. So let us now plug this into this formula right here. So on the left side, we have minus 2ka, and this has to be equal to minus 2m alpha divided by h bar squared, and this times psi of 0, but we already saw this is just going to be a. So from this we can now find our k. So this constant k, remember, this is exactly the same as we did in the case, for example, of the infinite square well, where we wanted to determine k because we know that k relates to the energy. So when we know k, we can find the energy. That's kind of something that we're really going to be doing very often in quantum mechanics. So, well, here we can simplify these 2's, the minus signs, the a. So in the end, we get that k is just going to be m times alpha divided by h bar squared. So we know that this is K. And our energy, as we defined at the beginning, was, let me go back and see where it is. There we go. We saw that K squared is minus 2me divided by h bar squared. So the energy then is going to be minus K squared h bar squared divided by 2m. So into this formula, we want to now plug in our values for K. So this is going to be minus m squared alpha squared h bar squared, which I will just write down as h bar squared times h bar squared times h bar squared divided by 2m. And here we can just simplify this h bar squared with this m with this right there. So we get that the energy is going to be minus m alpha squared divided by 2h bar squared. So this is going to be the energy of the bound state, or the way it should actually be phrased when you look at this, the bound state. As we can see, the value of the energy is unique. There's only going to be one allowed state, one bound state, nothing more, which is actually quite interesting. And now we can actually take a look at alpha and actually just go back a little bit and see, for example, when we determined this equation for the discontinuity, we saw right here the discontinuity is a function of this alpha. So if alpha is 0, which means there is no delta potential, we can see that the derivative will be continuous, right? Because the only reason it is not continuous is because of this delta potential. So that's actually, I think it's very cool to just go back and take a look at that. And here's, if this alpha were positive, sorry, not positive, but if this alpha were 0, once again, there is none of these delta potentials, then there is no bound state. This would just be a free particle where there are no bound states, only scattering states. So that is why that we just wouldn't have a solution in this particular. And well, as we can see, obviously the energy is indeed negative because all of these are just positive quantities with a minus sign. So we can see that it is indeed a bound state. So I think that is quite interesting, and that is the energy of this state. We still have to determine what are the wave functions of this state. So what we have so far is that our psi is going to be a times e to the minus k absolute value of x. Now we know what k is, so we actually could write this as a times e to the minus, I think k was 2m divided by h bar squared. Let me see if I got that one right. Yes, no, without the 2, it's m times alpha. Sorry about that, that's why I don't trust my memory. So this is just m times alpha divided by h bar squared, and this is going to be then times the absolute value of x. Okay, so we need to determine the constant of normalization now. So in order to do that, we are just going to normalize, as we have done many times in the past. So this is just going to be a squared times e to the minus 2. Instead of writing this, I'll just put it as k, right? There's no point in writing all of it the entire time. Dx. So now we have to integrate something with this absolute value in the exponential. We already did a problem on that in the past, and it's actually quite simple. All we have to do is divide this into two separate integrals, right? Because it's going to be different. Or we can just see, like, it to the two cases, I mean, positive or negative x, so that we can get rid of this absolute value sign. Or we can just say, oh, right, this is an even function over this symmetric interval. So this is just going to be twice the integral from 0 to infinity, right? Because it's the same from minus to infinity to 0 than from 0 to infinity because of this absolute value sign. So this is going to be twice a squared e to the minus 2 ax dx. Whoops, that looks like a k. I swear it's an x. Okay, so when we integrate this, we just get 2 a squared times e to the minus 2kx divided by minus 2k evaluated between 0 and infinity. So at infinity, this thing is just going to be 0. So we get 2 a squared minus 1 divided by to k. So this is just going to be plus, and this has to be equal to 1. So these two cancel out. So we see that a squared is just going to be k, so that a is going to be square root of k. And k, as we already saw, is just m times alpha divided by h bar squared. So the square root of this is just going to be that. So now we can finally write down the wave function for this alpha, this delta potential, and this is just going to be m alpha divided by h bar, square root of this. I just took the square root of h bar squared times e to the minus m alpha divided by h bar squared times the absolute value of x. And well, and then there are the energies that we already found. Let me just go back. I think it was minus m alpha squared. I think I'll just go back. I really don't trust my memory. Yeah, alpha squared divided by 2 h bar squared, right? Just double checking once more. Yes. So these are the result for our bound state, right? And so on what this is going to be, just to visualize it a little bit, actually I should go like this, considering that it's going to be more negative. We got this delta function here, and our these equations, these wave functions, are just going to be something a little bit like that, right? And this discontinuity will be because of the existence of this delta potential. And as we said, it's all going to be in the negative region, right? Because of the fact of the potential, I mean, because the energies are negative, because it has to be bound states. If we had taken these positive energies, which we will do in the previous video probably, then we would have these scattering states and our behavior will be different. So that is going to be it for this video. I hope you enjoyed it, and if there's any question at all, just let me know, and I'll see you next time.